All right, so what we're going to cover now is what I consider to actually be probably the most important two laws of what we're going to do in this class. And those two laws are called Kirchhoff's voltage law and Kirchhoff's current law. Sometimes people just refer to these as Kirchhoff's laws, okay? And the first of them, I'll get right into it, the first of them that I will cover is Kirchhoff's current law. It says that the algebraic sum of currents leaving a node must be 0. Now, I do have to confess, I arbitrarily chose the word leaving right there. I could just as easily have chosen the word what? Entering, right? But I chose one versus the other so that it wouldn't be confusing, right? You do, whenever you are doing an analysis using Kirchhoff's current law, you have to choose what direction you are taking to be positive, and anything that is the opposite of that direction, what do you do with it? You count those as negative contributions, right? So it's important that you sort of have mentally established what you are taking to be positive, which is why I chose one or the other of the ways to state it up here. Again, I could have just as easily chosen the word entering right there, but I chose leaving somewhat arbitrarily, okay? So what I want to do is just, first of all, for a circuit example like this, let's identify the nodes, right? Again, we can stick our highlighter on there and color as far as we can to all the extents up to each one of the elements wherever it stops. So that's one of them right there. I've got another one there. Okay, let me do another one here. And then finally, I have my fourth node that I'm identifying over here. So my point that I'm making right now is that we first need to know where our nodes are, and then we can look at the flows of current into or out of those nodes. And it should be that for any of the nodes that we identify, if we add up all of those flows in or out, they should sum to 0 as long as we take a consistent view of which one should be positive, like entering is positive or leaving is positive. So since I said leaving up here, I'm going to choose leaving as being positive and write a few equations that naturally pop out of a circuit like this. Okay, so I'm going to do the yellow node first. What equation could I write out for the yellow node using Kirchhoff's current law? I'm looking at currents leaving that node, right? So what would I have? Minus IA, because I have a current that I'm assuming is entering there for that, right? Then what? IB, is it entering or leaving? Entering, so that'd be another minus, right? Minus IB. Then I go to ID. Is it entering or leaving? It's also entering. So minus ID, I can say that the sum of all those currents has to be 0. Okay? Now, some of you are already might not really like that because you go, how can you have 3 negatives and then it equal to 0? Okay? Who has a response for that? Right. Any one of these 3 variable values that I put on there could actually have a negative value once we evaluate it, okay? Another way to say that is that what I'm showing here are called reference directions. It does not mean they have to be the actual direction that current is truly flowing. It's a reference so that you know how to interpret the values that are in the variables. Does that make sense? Okay, so then what would be another node that we could look at? Go to the blue one here. For the blue one, we're trying to look at leaving currents, right? So that would be positive IA, then what? Minus IC. Anything else? That'd be it. What do you get out of that equation, by the way? IA better equal IC, okay? Did we have any other way that we already knew that? A and C are on the same branch. Notice that? They better have the same current because they're on the same branch. Now what? Which other one should we do? Let's do green. Okay, we're looking at currents leaving, right? So I would have IB is leaving, all right? IC is leaving. IE looks like it's entering, right? So minus IE. What about IF? Okay, IF, it looks like it is also leaving. Oh, excuse me, leaving. Should be plus. IE is entering, so it's minus. Okay, so that's all the currents on that one, so I can set that equal to 0, right? That would be another valid equation according to Kirchhoff's current law. All right, just in the interest of completeness, we'll quickly do the last one as well. It looks like ID and IE both are leaving, so I'm going to take ID plus IE. What about IF? Okay, it's entering, so I'm going to take that as a minus value. Okay, let me make another couple points real quick before I leave the concept of Kirchhoff's current law. One is, you noticed here that I made all of my sign conventions for all four of these sums, I chose leaving. Okay? Did I do that because it was required, or did I do that to try to help not confuse myself? Okay. Yeah, you actually can, node to node to node, you can switch which direction you are taking to be positive, entering or leaving. I just don't recommend it, right? It's not illegal to do it. It's just, you know, I think choosing a particular way to do it and sticking with it is the most convenient way for you to not end up messing yourself up, okay? So once you, now I would say within a node, let's say I chose the yellow node, I don't want to switch halfway through that node, right? I don't want to be like, I'm going to do entering as positive at the beginning and then leaving as positive toward the end. Within a node, you do have to remain consistent within that node. But node to node to node, right? Like I go to a different node, I could switch which one I chose to be positive when I went to a different node if there was a good reason why I wanted to, right? So that's kind of one of those key points right there. And I think that's about all I need to say about Kirchhoff's current law. Questions on that one yet? Okay, let's talk about Kirchhoff's voltage law. Kirchhoff's voltage law says that the algebraic sum of voltage drops around any loop must be 0. Okay, so kind of the analogous thing to identifying nodes that we just did a second ago would be to identify some loops, right? Let me throw some on there, right? Let me put a loop down here. Let's say that's one of my loops, all right? Let me put another loop up here. And I won't be necessarily exhaustive in identifying all of my loops, but I'll put a few of them up here. There's 3 of my loops. Those 3 loops happen to also be meshes, by the way, according to our definition that we dealt with a little while ago. Let me put a 4th one on there as well so that I get one example of one that's not a mesh, because it's not required that it be a mesh in order to do a Kirchhoff's voltage law sum. And so let me put one, I'll just choose the one that goes maybe all the way around the outside of the circuit. How about that? Okay, and I can do sums on all of these as well. You will notice that I've already listed some of these voltage values across each one of the elements. Again, think of these as reference directions, right, where I've got the plus and minus on there. It's not saying that it has to be that direction in actuality. It's just giving you a place where you can interpret what the values are in the variables, the voltage variables there, right? Okay, so let me start with maybe my yellow loop right there. What would that sum look like? All right, we're doing voltage drops being positive, right? And in order for that to have meaning, we need to choose a direction that we are going around the loop. Like, we need to be consistent about what direction we choose, either clockwise or counterclockwise, but we need to actually pick something and stick with it as we go around there. So just arbitrarily, I'm going to say, let's pick clockwise, okay? And let's start down here where I have the little gap in my little loop, just because we got to start somewhere, okay? So let me ask you this. How much voltage drop do I have according to VA across element A? Let me ask you this. Is voltage dropping going that direction? If I'm going clockwise around through A, is voltage dropping or is it increasing? Right? According to reference direction A, right? Reference direction A assumes that it's increasing. So how would I count that contribution? Minus, right? So I would start with minus VA. Okay, then I'll go around up to B. How do I count that one? Same way, right? Minus VB. Then what? Okay, VE, the 2 terminals for that, looks like those are actually arranged the same way again, right? So minus VE. Okay. Anything else? Minus VC. Okay. Am I back to where I started? Yes. All right. That means that this sum has to be 0, according to Kirchhoff's voltage law. Okay? Not hard, right? Notice there, while we did that, all we really had to look at was what sign did our loop hit as we were going around? Like, what did we first hit on each one of those elements as we were going around? Notice I hit the negative sign first on VA. And then I hit the negative sign first on VB. And then I hit the negative sign first on VE. And then I hit the negative sign first on VC. That's a kind of a slicker and faster way to do these, is just say, well, which part of the polarity did I hit first as I was looping around? I'm going to take that as the sign in my sum. Okay? All right, let's do the next one. Do the blue one next. So the blue one, well, again, we'll start with that little gap right there. What sign do I hit first? Positive VB, right? It's the plus side of the VB. I loop around. What do I hit for VD? Positive. Then I keep looping around. What do I hit for VF? Negative. Not hard, right? Let's do the next one, green one. For that one, I will have VE. Okay. Then what? Positive VE, because I hit the plus first on VE. Then I have plus VF plus VG. Do I have anything else? So that, according to Kirchhoff's voltage law, had also better equal 0, that sum. Okay. Now we got one more, and it goes around the outside. And by the way, there are other loops I could have identified here. I just don't want to spend all day showing all the loops on all of this, okay? So let's say, again, start at the gap, and what's my first entry? Minus VA. Again, I'm going clockwise. Then I go to what? Plus VD plus VG minus VC. That gets me back to where I started. Okay? If I did any more, it'd be boring. Some of you might say we already passed that a while back. Okay? So, but there's not actually that much more to say about Kirchhoff's voltage law, right? And there's not that much more to say about Kirchhoff's current law. This is how they work. They are incredibly powerful, though, right? We can actually use these for many, many purposes. As a matter of fact, the next several lectures, I think of them as being corollaries of Kirchhoff's laws, right? We're going to talk about several other methods that we can use in circuits. To me, they are just essentially extensions of things that come about because Kirchhoff's laws work the way that they do. Okay, so they're very, very important. What we're going to do now is a couple of examples. Okay, the first example is this one right here. It says, find the current flowing in each resistor, and then it asks, how much power is dissipated by the resistors? Okay, we can do both of those questions, right? All right, so where do you suggest we start? All right. A really good place to start if you don't know what to do is go ahead and identify your nodes. Okay? So for this one, let me get one of my highlighters and start coloring one of my nodes. I'll do the one on the kind of the inside of all of this stuff. Because they're all connected there at the middle, those would all be parts of that middle node right there, all colored yellow. Okay? And I think I hit elements everywhere I could go there, so I think I got the extents of my first node. What about any other nodes? Okay, I drop my pen somewhere else on here, and I start coloring in every direction until I hit an element in every direction. Okay, I think that did it. We've now got our nodes identified. Based on something you've heard recently, is this a circuit of a particular type? This is a single node pair, right? There's one pair of nodes that I have for this circuit, okay? One of the things that you know as a result of that is that every element has the same voltage across it. Okay? Because there's only going to be one voltage across a pair of nodes, right? And those pair of nodes actually hit every single one of these elements. The other way to say that is that all of these elements are in parallel with one another. Okay? So those are some interesting things to note. I don't know that it necessarily helps us solve the problem, but it actually is an interesting thing to go ahead and note. We'll see whether or not there's good stuff we can pull out of that. All right, what do you think might be a good tool to use to solve this problem? Okay, based on maybe the topic of this lecture. Okay, one of Kirchhoff's laws is a really good guess. Let's use Kirchhoff's current law. How about that? Okay, KCL. Okay, and when we do KCL, we got to pick a node, right? So which node do you want to pick? Okay, we could pick the outside. I actually like the inside. I'm going to pick the inside. Sorry, I shouldn't have asked if I was going to do what I was going to do anyway. So, all right, I want to pick the inside. It doesn't matter. We could pick either one of them. They could both work. It's easier for me to look at the inside one. All right, so, and we have to pick a direction to be positive. Okay, and to be a good example to you here, now that I have chosen, my very first time I said leaving is positive. I am probably never going to depart from that. Okay, I'm going to do that pretty much every time. So leaving is positive. Now let's go through each of our elements and figure out how much current leaves the yellow node on each one of the branches of this circuit. Right? The branches are the things that go across from one node to the other. Okay? And there's a really, let's say I start on this 1 amp current source. That's a good place to warm up, right? How much current leaves that node on the 1 amp current source? 1 amp. Great, that's awesome. Now, the way that I can deal with some of these other things, maybe, is that I could actually identify some currents that might flow on each one of these things. And so what I'm going to do here is, based on knowing that Vx has been labeled over here, see that? Vx is labeled. What direction would current flow in this 35 ohm resistor? If we know, let's say we assume Vx really does go that direction, like the actual voltage is that polarity. In other words, Vx would be a positive number. What if we assume that? Do we know what direction current should flow? Okay, should flow left to right. Let me put that on there as a variable, right? And I'll call that maybe I-35 or something like that to kind of indicate that that is a current that flows right there. Okay, let me do that element next in my sum, right? So I would have I-35 not leaving the node, but entering the node. So I would say minus I-35. Okay? Because I get to choose. Okay? His question is, why did we say it's entering? Or maybe I misunderstand your question. The reason that I-35 has to be entering is that that current goes that way. So it enters the yellow node. We're summing currents into and out of the yellow node. So that current, if I say it's going that direction, is entering that node. Okay? Now, keep in mind, these are reference directions because I-35 might end up having a negative value. Right? So it might not actually be going that direction, but I need to pick something and stick with it when I do my sums. Okay? So, what's the next one? If I just keep going around that direction. Okay, 3 amps entering. And because I'm taking leaving as positive, I'm going to take that 3 amps entering as being negative. Now, I did that little thing with I-35 over there for the 35 ohm resistor. Can I do something similar for the 15 ohm resistor? I could. As a matter of fact, I can even do better than that. Because we have a common voltage across all these elements, I can even say that for the 15 ohm resistor, this had better also be Vx, right? That has to be, if this one's at Vx, they go across the same two nodes, they better be at the same voltage. Those two nodes better be at the same voltage relative to each other. Okay? So if that's the case, then I should be able to identify a current going this way that is I-15. Right? And if that's the case, I should be able to take minus I-15 in my sum. Now what about the dependent source we are now around to? It looks like it's leaving, right? And so we'll count that as being plus or minus. Leaving is positive, right? Not entering. Okay, so plus 1 over 5 ohms times Vx. Nothing extra special there. Okay, then what? Can I do something similar for the 25 ohm resistor as I did for the 35 and the 15? Okay, yeah, keep in mind I can still label the voltage if I want to do that. That's Vx. It's going to be across the same polarity as the other two, you know, plus to the blue side, negative to the yellow side. And once we put that on there, we can see that current is likely to flow that direction if Vx is positive. And so we'll have I-25 that I show right there. How do I count that in my sum? Minus. So minus I-25. And have I accounted for all the paths that can enter or exit the yellow node? It looks like I have. You got a question? I chose the direction for I-35, I-15, and I-25 so that it was consistent with my assumed direction for Vx. So in other words, if Vx turns out to be positive, then I-35 will also be positive, and I-15 will also be positive, and I-25 will also be positive.
But is that based on some principle, or is that something that we chose?
Hypothetically, you could flip those, but you would have to then keep a note somewhere in the back of your head that would say that I-35 and Vx don't directly obey Ohm's law. There's an extra sign you got to put in there, right? So, you know, I could put that label on there, but by me labeling this way, I will not have to do anything extra beyond just use Ohm's law, because I chose to make their directions consistent as I labeled them.
So is it always going to point into the positive for the sake of?
Ohm's law would indicate that you always are going to have, if you know, you have current flowing from left to right on a resistor, then the left one is going to be plus and the right one's going to be minus. Yep, that's a consistent thing that will always be. Okay. So we just got finished saying that we accounted for all the paths in or out of the yellow node. So what can we do with this little sum that I've been making? I can close it off. Now, it's actually a good segue talking about Ohm's law, because as I look at this equation, how many things do I have there that I don't know? 1, 2, 3, 4, right? I don't know Vx, I don't know I-35, I-15, or I-25. But I have more relationships that I can bring in from Ohm's law, right? I can look at I-35, right? And I can say, based on the fact that I-35 flows into the positive terminal here and that I've already given this a variable of Vx, I can rewrite I-35 as what? Vx over 35 ohms. Right? Ohm's law says that because I know the voltage across there and I've given a variable to the current, all those are relationships that are established, I guess, is what I'm saying there, right? So 1 amp, I can rewrite this equation now where I take I-35 and replace it with what? Vx over 35 ohms, right? 3 amps I don't have to do anything with, but what can I do with I-15? Vx over 15 ohms. What can I do with my dependent source, or do I need to do anything with my dependent source? Okay. Doesn't really need to have anything done with it, right? 1 over 5 ohms Vx. And then I get up there to my I-25, right? I-25 can be rewritten as Vx over 25 ohms. So now how many unknowns do I have in that equation? It looks to me like I'm down to 1, right? 1 unknown that makes us happy, right? 1 equation, 1 unknown, big smile on our face. Okay, so some of you might already be familiar with this, but in case you're not, I'll show it. I won't always do this in all of my lectures, but once you have something that is expressed as a single variable equation, your calculator has a nice tool that you can use. You can enter that equation directly. In this case, I'll do 1 minus, instead of Vx, I'm going to call that x. Okay, so x over 35 minus 3, okay, minus, I'm still going to use x for Vx, right? So I'll put x in there like that, divided by 15. Here I'm going to do plus, right, x over 5. And then my last term there, I'm going to do x, oops, I needed to do a minus there first, x over 25 equals 0, right? So I don't necessarily need to manipulate this equation by hand or anything like that. I can just directly put that in there and hit solve. And it will tell me what that Vx value has to be. So it's 30.88. What will those units be? Okay, if you look at the units that were a part of the original, right, I had amps and ohms, right, and nothing outside of base units, so there's really no expectation I would have that this is going to be anything but volts, right? So 30.88 volts. Now my question here is that what we were supposed to find? All right. Well, maybe not, but it might be a really important stepping stone along the way. What are we supposed to find? Current flowing in each resistor. Okay, how do I get there from knowing this voltage? All right, shall we start on the 35 ohm resistor again? Okay, we wrote an expression right here for how much current flowed in that resistor. Remember, we had I-35 was equal to Vx over 35 ohms, so I'm going to say I-35 is going to be equal to Vx, which was just 30.88 volts, divided by 35 ohms. Right? Now let me show you another nice thing with the calculator. After you have done this step right here, it actually has that number stored in variable x now. Okay? So if I want to, I can pull that variable back out and divide by 35, and that gets me what current I have flowing on my 35 ohm resistor. It's going to be 0.882, and the units will be amps. Okay, so that is my answer for I-35. What else does it ask for here? It says how much power is dissipated by the resistors. How do I find that for I-35? Let me call it P35. You could do that P is equal to IV. Since we now know I and we know V, we certainly could do that. What other relationships could we use if for some reason we didn't know those? Yeah, it actually works out very similar to what I just did, the only difference being I would square that voltage and then divide by the resistance, right? 27.25 or so watts. Yeah, the formula there, what I did basically there was I took 30.88 volts and squared it and divided by the resistance value, 35 ohms. That was your V squared over R formulation that we looked at just a little while ago. Okay, cool. What about the next one? Do I-15. I-15 will just be 30.88 volts over 15 ohms. Okay. So no difference here other than, got to get rid of that square again, and then go over here and do 15. 2.059 units. Again, it'll be amps, right, for that current. Now what about P15? Again, we can use that V squared over R. All I have to do is go in here and square that X, and that will get me 63.58, and that will be in watts. All right, now what about my last one, I-25? Again, no difference, 30.88 volts divided by 25 ohms, and we will have 1.235 amps. Okay, and the power for the 25 ohm resistor is simply going to be same equation, but with X squared, 38.15 watts. I won't bore you with it. If you're curious, the sum of all those powers that are dissipated by the resistors wound up being 129 watts or so. That would be how much is dissipated in resistors, right? That doesn't count the sources. Okay, let's do one more example, and then we'll get into the other stuff that we do. This says, find the power supplied by the dependent source. Also determine whether each of the other sources supplies or absorbs power. Okay. It gives us several sources there, right? We got one dependent source and two independent sources. Then we've got three resistors, it looks like, 50 ohm, 30 ohm, and 40 ohm. Where should we start? We could identify some nodes, okay? I don't have a problem with that. Let me start here. There's a node. Here's a node. Here's a node. Here's a node. Going to run out of colors here. Let me get another color here. There's an orange node. Okay, I need one more color. Let me see. How about pinky? Now, we identified our nodes. We have several of them. There's quite a few of them. Do each one of the nodes kind of have a similar look to it? Let me ask this. Do any of the nodes appear as though there's a place where current can split? Okay, so how do we interpret that piece of information once we notice that there's no place where current can split? Okay, this is a circuit in a particular category called a single loop, right? Now, when you have a single loop, what does that mean in terms of the current in that loop? It will be the same current no matter where you look in that loop. It's going to have the same current, right? So where I have that current IX identified over there, we could actually chase that around, and that IX is going to be right here. It's going to go right through here, right? It's going to go up through here. It's going to go down through here. It's going to go across there. It's going to go up here. And it's going to go down through there. And all of those little arrows that I just drew are all I sub x, right? Because there's no other place for current to go, right? There's one current in here, and it's the same no matter where we look. Okay? Well, that might be helpful. Where do you want to go next with this? Okay? How about this? Since there's one loop, since there's only one loop, it sounds like maybe KVL might be a good strategy for us to use, because there will only be one of those that we need to write, right? The sum of voltages around any closed loop, around any loop, has to be 0, right? So we only really have one loop here. Let's sum the voltages, okay? And in the interest of time, I'm going to condense one of the steps I did on the last example, right? You might have noticed on the last example, I labeled voltages on every single one of my elements. The analogy of that to this problem would be labeling currents right, everywhere that I went. And then, you know, actually up here in this example, right, I labeled these currents, right, and then I said what those had to be relative to voltages. Okay? Down here, I could, if I wanted to, label voltages on each one of my elements, put that into one sum, and then do a second version where I apply Ohm's law to all of my resistors. Or I could do that in one step. So I'm going to show you doing that in one step now, and I probably will do that most of the rest of the class, right? If it's an Ohm's law relationship, I probably won't do it in a separate step. Yeah, I'll put it in whatever form I need it and just understand that it was Ohm's law that was what got me there, okay? You'll see what I mean when I get through this, okay? Where do you want to start in the loop? I don't really care. Tell you what, I'll go down to the bottom left corner, and we'll start with the 50 ohm resistor. Okay, I have IX flowing through the 50 ohm resistor. That will create what kind of a voltage on the 50 ohm resistor? IX flowing through 50 ohms makes what voltage? IX times 50 ohms. Okay, now because IX is flowing this direction, and I'm doing a clockwise sum, and I'm counting voltage drops as being positive. Okay, I'm going to do a KVL right here, just to want to label it, right? Doing voltage drops as positive. The 50 ohm is going to have a positive voltage across it going this way, right? It's going to have its polarity going that way if IX flows the direction I'm showing. So if I want to say what the voltage is across there in terms of IX, the voltage drop is just going to be positive IX times 50 ohms. That's what that first voltage drop is right there. Then I go up to my 60 volt source up there. How much voltage drop happens there? 60 volts. You'll notice I'm counting whatever sign I hit first as I progress around the loop. I'm counting whatever sign I hit first as being my positive, or excuse me, as my sign that I use in the sum. Okay, then I go up to the next one. How do I count that? Plus 10 ohms, IX. Then what? Plus IX times 30 ohms. All right, that would be the next one. Then I go over here. How do I count the 20 volts? Minus 20 volts. Then I go to the 40 ohm. Okay. Then I go into my orange node down there. Do I have anything else? Now you'll notice, you know, the spots where I did Ohm's law just by inspection would basically be any place I have the IX times 50 ohms, or the IX times 30 ohms, or the IX times 40 ohms. I did Ohm's law just by inspection on those and inserted that value into this sum instead of having a separate step of first labeling the voltage and then telling you what the voltage would be according to Ohm's law. That make sense? Okay, now this equation that I have written, how many unknowns do I have in it? One unknown. Okay? And so if we want, we can do the same kind of steps I just did, right? X times 50 plus 60 plus 10 times X plus 30 times X minus 20 plus 40 times X is equal to 0. And when I put all that in there, X turns out to be negative 0.3077 or so. That would be IX, right? IX ends up being negative 0.3077, is that what I said? Amps. What does the negative mean? Okay. Yeah, it means that my IX that I originally identified on here, right? It means that the true direction of current really flows opposite of the direction of that arrow, okay? It does not mean that you need to flip everything around. You can actually interpret this properly by saying IX reference direction goes this way and IX value is negative, and that is clear enough. So there's that. Is that what we were supposed to find? It says here, find the power supplied by the dependent source, right? How do we do that? The dependent source is not a resistor, correct? So I need to simultaneously determine the voltage across the dependent source and the current through the dependent source. If I know those two things, then I can determine how much power is being supplied by the dependent source. With me? All right, so let me do this. Let me actually sort of separate off the dependent source just so we're not confused by stuff. Let's kind of think of it all by itself over here. Do we now know which direction current flows through the dependent source? Okay, the dependent source has its polarity like this, right? And we know that the current that flows through it actually doesn't go the direction we assumed originally. It really is going to go the opposite direction, right? It's going that way with a value of 0.3077 amps. Agree with me? Okay. Now, what value is this going to be as a voltage? 10 ohms times Ix. When I do this, I have to keep my sign of Ix. Okay? Because there's nothing that tells me I can get rid of it. I assumed it was, Ix, because Ix turns out to be negative. I have to keep that sign whenever I calculate this. So once I calculate this, it's going to end up being negative 3.077 volts, right? Negative 3.077 volts. What does that mean? That means the same thing as if I came in here and flipped these terminals around and made this a positive number. Would you agree with that? So this is the actual directions of what's going on with that dependent source. So my question is, does it supply power or does it absorb power? Okay, I hear several people murmuring absorb, and you are correct. It is absorbing power. How do I know that? Okay, the current arrow is flowing into the positive side, and when that's the case, we have a case of absorbing power. Okay, this told me to find how much power is supplied by the dependent source. So how do I determine that? P supplied in the dependent source. Okay, so that's going to be actually minus 3.077 volts times 0.3077 amps. Okay, why minus? Actually, it might be more clear if I put that parenthesis in there. Why is it minus? It's minus simply because the question asked me to find the power supplied. So I have to make it negative of whatever it would have been absorbing. We looked at it here and said it is actually absorbing, so that would be a negative power supplied. Does that make sense? So anyway, if you plug that in, I won't do it formally in the calculator, that ends up being negative 0.9467 watts. That would be the power that would be supplied by that element, which basically means that 0.9467 watts are being absorbed. Make sense? All right, the last part of this was also determine whether each of the other sources supplies or absorbs power. Okay, how do we do that? Okay, let's actually take each one individually, right? With the 60 volt source, it's got 60 volts going this way. What direction does current flow? Turns out it actually flows left to right, correct? Even though we thought it was the other way at first, right? It actually goes left to right that way at a value of 0.3077 amps. Okay, so what is that source doing? That source is supplying power. Okay, what about the 20 volt source? This one has 20 volts like this. What direction does current flow? Really, it goes this direction, right? 0.3077 amps. Okay. Does it supply power or absorb power? This one is absorbing power. That make sense? You can say no if you want. We can talk about it, but hopefully it makes sense. All right. That's all we have for today. Shall we do our in-class assignments?